So we're now thinking about trying to describe a plane in space and creating maybe an equation to describe it. So as we think about doing that, planes in space are uniquely determined by a point and a normal vector. So let's take a look at why that might have to be the case. So let's consider this plane. It kind of looks like a sheet of paper, but it is a plane, and think about it as extending infinitely in all directions. And I have this point P that's in the plane. And so the P, the point, will fix the plane in space. Okay. Now if we think about the number of planes that can contain that point, think about the number of sheets that you could have that would pass through that point. And it should become somewhat clear that there's actually an infinite number of planes that could contain that point. So a point isn't sufficient, and we could maybe think about having a vector in the plane, but if we have a vector in the plane, notice we have some problems because there's an infinite number of vectors in a plane. So having a vector in the plane will not create something that is unique for us, and we do want it to be a unique situation. But if we think about this plane and it's a flat object, we can see that if I want something perpendicular to the plane vertically, something like that, that could be potentially unique. The only reason I say potentially is that there is another normal vector to that plane, and it would go down below something like this, but it would also be normal vector. Now, normal vector should bring to mind the idea of a 90-degree angle to the plane, and it's a relationship that is similar. So this is a much better situation than trying to use a vector in the plane, because we can see that through that point, and given that normal vector, there's really only two possible directions, and both of them are normal, so those we're going to deem as being good enough. So we'll need a point in the plane, and we will need a normal vector to be able to write the equation of a plane. So we're ready to start thinking about the equation of a plane. So assume we have 3 points, P, Q, and R, in that plane. And how can we find the equation of that plane? So first of all, we need to remind ourselves we need a normal vector, and we need a point. Well, I don't have a normal vector, but by golly, I've got 3 points. So I have sufficient number of points. In fact, I've got more than I need, but I do not have a normal vector. So then the question becomes, can I use those 3 points to create a normal vector? And the answer to that question is yes, I can. Consider using those points to form 2 vectors, the vector PQ and the vector PR. So PQ has an initial point of P and a terminal point of Q, and shares the same initial point P with the vector PR. Now we've studied the cross product, and we know that the cross product creates a new vector that is orthogonal or normal to the original 2 vectors. So if I take those 2 vectors I created from my 3 points, vector PQ and vector PR, and I do a cross product, I will get a vector that is orthogonal to both. And note I've changed the order of that cross product because following the right-hand rule for cross products, the normal vector that I have drawn is actually PR cross PQ. Does it really matter which normal vector I use? No, I can use PR cross PQ, or I can use PQ cross PR. So now I've determined that with the information I do have, I can create a normal vector, and I have a point that I could use. So now the question becomes, how do I actually write the equation of the normal of the plane? Now, for simplicity's sake, we're going to think of this normal vector, whichever form we use it in, as having three components, A, B, and C, to help us in our writing of the equation. So now as we think about writing an equation of the plane, we're going to pick an arbitrary point in the plane, just like we typically do with a line. We have an X and a Y. Well, we're going to have, that should be X, Y, and Z, not X naught, Y naught, and Z naught. So please ignore those subscripts. But over here at point P, and it doesn't matter which point I use, these are the points X naught, Y naught, and Z naught. And these are just X, Y, and Z. And we're going to make another vector from this point, this arbitrary point, over to point P. Now, this arbitrary vector has components like this vector. I misspoke. That's from P to our arbitrary point. So P to X, Y, and Z. So the components of this vector are X minus X naught, Y minus Y naught, Z minus Z naught. So our vector here that we just drew is in the plane, and it does have this orthogonal perpendicular normal relationship to that vector we created from PR cross PQ. So that means that if I take vector PR cross PQ and I do a dot product with that new vector, because they're orthogonal or perpendicular, that should equal 0. So we said we would, for simplicity's sake, call this vector ABC, and we're doing a dot product, X minus X naught, Y minus Y naught, and Z minus Z naught equals 0. And if I actually do that dot product, that is, multiply corresponding entries of the vectors and add together, I get A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals 0. And this is known as the point normal form of the plane. And the standard form would come about by actually multiplying this out and then combining like terms.